Alright, my computer just crashed. Hopefully it doesn't crash again. That'd be very unfortunate. I'm currently working on getting a new computer because this computer has been acting very off recently. So, yeah. Hopefully it doesn't happen again though. All right, let's get back then to looking at what we were looking at before, which was level 5. And we were looking at, we're getting ready to look at confirming what we were discussing in terms of how this authorization flag works. But I'm thinking now let's just to save a little bit of time, let's assume our assumption is correct, that the first 8 bytes, if it's non-zero, and then we did like a read flag, somehow made those first 8 bytes non-zero, and then did a puts flag, that we would in fact get the flag. Let's assume that our reverse engineering skills are correct. Of course, if we continued to have issues as we went along, we would definitely want to further investigate and double check to make sure that we're not off on that, our ability to reverse on that. Okay, so we were looking then to, okay, so the thing we want to do, actually, hold on, do we want to show it now? I think we've done enough reversing in binary ninja. Let me hide that now, so we can just see the terminal. There we go. Oh no, that's not the right one. This right there. Yeah, okay. So, what we were saying, just to say it for I guess the millionth time, is that we want to do a read flag at this address. The first 8 bytes, we want to somehow make them be not 0 because it zeroed it out. And then when we do puts flag, it tells us not authorized because the first 8 bytes in here are 0. So we just need some sort of primitive or some sort of ability to write that will allow us to make the first 8 bytes of this something other than 0. Okay, so what are the things that we have access to then? So in terms of from an ability to write to memory perspective. So I'm looking here. So puts is going to definitely just output data. I'm not sure if you can convince that to do a write. Maybe there's some insane way. But this definitely doesn't immediately stand out as something that would let us write. Read flag, puts flag, probably not. Maybe we could trick them. Yeah, so puts flag is probably going to be the same as puts in terms of our ability. Maybe read flag we could somehow, because we know that read flag is going to write the flag to memory. So maybe one line of thinking would be if we can write the flag to memory, can we maybe write part of the flag to that first 8 bytes to make it non-zero, and then now we have now we would have made it non-zero, but then we can take our original read flag buffer and try to puts flag it. There's probably some version of that could maybe work, so that's something to keep in mind. But definitely sounds a little tricky. Maybe another line of thinking is that when we do this read flag, we just completely ignore this puts flag, and that somehow we can convince puts to puts at an offset into read flag, because we know that after we do this, the flag is loaded in memory 16 bytes later. So if we could somehow set up a malloc and using malloc and free in the heap, somehow convince basically to get two overlapping-ish chunks where you have one chunk that would be right here at this flag buffer address, and another chunk that would be 16 bytes later. And then if you had that situation, you could then free the first one so that when you did read flag, you would get this same buffer, but you'd still also have something pointing to 16 bytes later, and you'd be able to puts them. So that's definitely a line of thinking, I guess, to think about. But there's actually a significantly easier thing to be thinking about here. So as it turns out with all of these challenges, I'm describing some things that I think probably could work, but definitely sound pretty complicated. And the goal with these heap challenges isn't to get too super crazy into heap. So heap can have a lot of all sorts of weird niche things you can do, and I don't know, if you look into like the Shellfish's how to heap and look at all of the house of blah things, you will see that there's all sorts of weird techniques, some of which will do this like overlapping stuff that I'm discussing. But a lot of these house of whatevers only work in certain libcs, and it gets kind of complicated. So we're kind of looking in these challenges at kind of the basics of how Tcache works. And I keep saying in Discord, I keep saying like embrace the linked list. So everything, all of these challenges that we have released, they just have to do with some basic linked list principles. So what do I mean by that? Okay. So Tcache, actually, let's quickly attempt to use Paint real quick, because I think it will hopefully be useful. Okay, okay. So how does Tcache work? So when we call malloc, we get a chunk of memory that is approximately the size of what you ask for. It's a bit bigger to account for some metadata, and also the multiple different size chunks get coalesced into being the same size. But either way, you get a chunk of memory. And you can do whatever it is that you want to do with this memory. But you also, as part of this allocation, something to point out, is that there's some data sitting before. So when you call malloc, you have, this is what malloc gives you basically. It's the contract you have with malloc is that you are going to use this memory. In fact, actually, let's even be a little bit more clear to illustrate what the contract is with malloc. So malloc says you can use this memory. So if I ask for, I actually don't know the coalescing sizes off the top of my head. Let's assume 16 is the first bucket size, that malloc will at least return you 16 bytes worth of data. But let's say you ask for let's say you ask for 12 bytes. So these 12 bytes here are yours to use. Do whatever you want after you malloc, just use it however you please. There's also going to be some extra bytes. So let's say we asked for 12, but it rounded it up to 16. There's going to be these 4 bytes that have to do with basically it rounding the size up. Whether or not you can use this, I'm not sure what the official documentation says, that if you ask for 12 bytes but you get 16, are you allowed to use the 4? You probably can use it, but I don't know. This is kind of a gray zone. If you wanted 16 bytes, just ask for 16 bytes. But technically it will round it up and give you a bit more, just to so it basically wants to, it's going to be maintaining these linked lists, and it doesn't want a linked list for literally every possible size. It wants like groups of 16, and it'll just round it up and give you that. But okay, but the other thing it gives you kind of, it doesn't really give you this, but is associated with it, is this metadata over here. So when you call malloc, the pointer it's actually going to give you is right here. And you can do as you please with this, but in order for malloc to track what's going on, it actually stores, and specifically, yeah, so it actually stores some more data up here right before the pointer it gives to you. It gives you a size and a previous size. So maybe we'll just draw like a line here. So it tracks how big it is, how big this malloc chunk is that it returned to you. And it also tells you how big the previous chunk allocated, previous being like in this potentially like linked list structure, whatever, there's previous size. But either way, you might wonder like, why does it do this? Why does this matter? So the reason it matters is that it's storing this data so it knows what to do when you call free on it, for instance. So when you eventually go on, you use this data and then you decide you're done with it, you don't actually care about it anymore, you're basically telling the heap, I will not use this data anymore. Go ahead and take it back because I'm done with it. You're kind of promising that you're done with it. Theoretically, you could still use it, as we kind of discussed with this heap misuse and a use after free. But the heap assumes you're an honest person and that you are done with it and that it can do whatever it wants with it in terms of giving it out to someone else. So the reason it keeps track of this size is that, so let's say here we got our 16-byte chunk and then we call free on it, and by calling free on it, we're saying we're done with it. It is now able to, so let's say that this is, we'll just kind of call this, oh god, malloc. Yeah, writing is impossible with the mouse, but let's just go with it. And let's make this arrow a little bit smaller just to give ourselves some more room. Okay, so now we call free on this pointer. So why is it keeping track of the size? So we call free. So what free is going to do is it's going to actually look at this size right here, this 8 bytes right before the pointer, and it's going to use that and say, okay, this was 16 bytes. We can store this in this linked list structure. In this case, we're looking specifically at Tcache. This Tcache linked list, and we can basically say, so let's call this pointer, let's just call it A. After we call free on A, we can basically, so in fact, let's just show that linked list, or that Tcache has multiple bin sizes. So let's say that the first one here for this is for the size 16. Oh god, this is awful. Okay. So let's say this one's for 16, and then maybe this one's for 32, and then this one's for 48, and so on. So we called free. It goes back and looks at what's the size of this free. It says it's 16. So it says, okay, I'm going to store this address in our Tcache linked list. I'm going to store it at the bucket for size 16 because we just determined this is of size 16. It's not size 32, it's not size 48, it's not something else, right? It's size 16. So we're getting ready to set up, let's assume for this example that we're walking through in Paint that nothing else has been freed so far, that basically this Tcache freed linked list setup is just, imagine that these are all just nulls immediately, right? So basically you can think of it as it's an empty null linked list. When it's null at the start, and you call malloc, it can look up in here and be like, oh yeah, there's nothing there, so we need to use some other mechanism to get memory. Okay, but so we called malloc, we got somehow, just assume somehow that Tcache is empty, some mechanism allows us to still get memory even when Tcache is empty, and that's what it gave us A. But then we call free on A, and now we begin the Tcache linked list. A gets stored in this Tcache header. So let's specifically focus on for size 16. So what do I mean by this like Tcache header? So think about a linked list, right? So a linked list, you're going to have a pointer that is basically the head of the linked list. And what I'm saying is that this head is going to be now A. Whatever this address was that Malik had been given to it, or that Malik gave us, and then we called free on it. So now the header is A. So what does that mean? What that means is that now if someone else calls Malik on 16, so say we continue on and call Malik on 16, it's actually going to give us A. So it's going to give us A, and then what else is going to happen? So this is what the challenges are all about. What happens in this Tcache linked list structure? So we get A, and this is important to note. We know why we got A. We got A because this is what's at the head of this linked list. But more happens, right? It's not just that Malik returns A. More stuff happens. What other stuff happens is that the Tcache linked list has to be updated. And what does it get updated with? Well, it actually, or maybe this is, maybe I'm jumping a little bit too far ahead in terms of, yeah, there's a question in Zoom, go for it. It's what would be in your mind the heap list? No, so all we need to keep track of is what's available. We don't necessarily need to keep track of what we've given out per se. We just, I mean, you could think of them as like, if you know what's available, then you know what's not available or whatever. But all we're keeping track of is what is available to give out next time someone calls Malik. And this might be empty, as I said before. And when it's empty, something other than Tcache happens in order to give out this memory. But when it's not empty, when it has data in here, it's going to give that out. Okay, so I was saying we're kind of getting a little far ahead by just doing Malik free and then Malik, because it's kind of difficult to illustrate exactly what's happening. It'd probably be better if we said Malik, Malik, and then free, free. Okay, so maybe we should use text instead of trying to write with a mouse. Let's go with size 36. Maybe that'll be readable. Okay, so let's say we call Malik 16, and that gives us A. And before I was saying, oh, that scroll's weird. Okay, before I was saying 12, let's just go and assume we actually asked for 16, rather than continue to discuss this like rounding up phenomenon. So let's say we call Malik 16, it gives us A. And then we call Malik 16 again, and it gives us B. How do I want to do this? Maybe I should switch to like a text editor. Am I going to be drawing? Let's see here. Let's use, I guess we can do the following. We can still see, looks like, how does this look on stream? Let's see here. Say that again? Yeah, the issue is I just want to write stuff. Hello, test. Please move window away from shared app. I don't know who's complaining about that. It doesn't seem like OBS cares. I don't know if Zoom is complaining about stuff right now or what. Okay, let's just roll with it. Hold on, let me leave Emacs real quick. Let me zoom in 2 more times just to make sure this is very readable on screen. Hello world. Does this show up? I want it. Oh, let's go even more. Hello world. Why? 1, 2, 3, 4, 5. Hold on. Is this actually even making it bigger on stream? Oh, maybe it was actually. Hold on. Okay, let's go. Let's go crazy then. Hello world. Okay, I'm gonna assume that this is reasonably, this can be read reasonably well. Okay, so what were we doing? So we're going to now use Emacs instead of Paint to write text, because writing text in Paint is a little awful. And yeah, it turns out Emacs might actually be a better text editor than Paint. So we are going to start talking about this Tcache list. Okay, so what operations are we interested in understanding for how it influences Tcache? Okay, so let's say we call, let's say we call malloc16, and that gives us address A back. And then we call malloc16, that gives us address B back. And then we call free A, and then we call free B. Okay, so the thing to represent is our Tcache, and let's say for like size 16 or something. I don't know, maybe we'll use this notation. Okay, so Tcache of curly brace size 16 or whatever, let's say that initially, before we do these operations, that this is null. Okay, so what does it mean when this is null? So I keep saying that somehow we get A, somehow we get B, and let's continue to say that. But when we call malloc16, the first thing we do when we call malloc16 is we look at this and see, is this non-null? If this is non-null, then somehow we give ourselves memory in a different way. And in this case, it gives us A. And then we call malloc16 again. And then we check Tcache. Is it non-null? Yeah, sorry, it's null. So we're going to have to use some other mechanism to get memory. So we get B. Okay, now stuff starts to happen. Now we call free A. Okay, and let's actually represent also kind of what A looks like in memory. I'm trying to think of like notation to use that's the least confusing. We'll use like this, and we will use like prev size, or let's just use like 2 dots to denote that there's some metadata. Or no, that doesn't sound that good. Let's do this. Let's do dot this. And then let's go with, oh, we're using A already. Let's go with S. 4, 5, 6, 7, 8. And then is this 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and what is A? A points to right here. Okay. Maybe this is going to be an okay-ish way to show this. And then what is B? Let's assume it's similar, but let's actually, well, okay, so initially A is, who knows what data is in here, right? So I've kind of denoted here 16 bytes worth of data. And then we just put like these 2 dots to denote that there's some metadata, and we use this to say that A is pointing right here at the beginning. Or maybe we should say that's the beginning if we want to be like 0 based or whatever. But yeah, so basically A is pointing here, and B is pointing here. And we have some amount of memory, so we called malloc, we got A, we did whatever it is that we wanted to do with this memory. Who cares what we did with it? As far as malloc is concerned, it doesn't care. It's our memory to use. and then we called malloc 16 again, and we got B, and B does whatever, program does whatever it wants with this memory as well. It's only once we free it that this becomes relevant in terms of the heap. Okay, so what happens now, finally, after rambling for several minutes, what happens once we finally call free of A? So when we finally call free of A, the following is going to happen. This is no longer needs to be null. Now we have the ability to say that A lives in the T cache. It's ready to go. Someone that wants to call malloc later on, for size 16, can use us. So what's going to happen here is that this becomes A. And remember that this is a linked list. And to say that it's a linked list means that all we need to do in terms of the header of Tcache is keep track of a single pointer. Because a linked list is this recursive data structure where the head needs to just keep track of one pointer, and then the pointer keeps track of the next pointer, and the pointer keeps track of the next pointer recursively, right? So what happens here? When we call free A, so this is the operation we're currently looking at. Let's actually just get rid of that for video purposes or whatever. When we call free A, what's going to happen is that, so before we had this 0, it becomes an A, and then actually some of this data, in fact, all of these 16 bytes are going to get overwritten for the purposes of Tcache. What are they going to get overwritten with? They are going to be overwritten with, in this case, the next pointer. Who is next? So these S's are going to become zeros. 4, 5, 6, 7, 8. Okay, so why do these S's become zeros? Because this first 8 bytes here keeps track of the next pointer. And what is the next pointer? Well, the next pointer is whatever was previously here. So we previously had a 0 here. So we actually take this 0. You can kind of imagine we like rip it out of the head of Tcache. In its place, we put A. And then we take what was previously located there and we shove it here. And now we've done our linked list operation. Okay, so what is, yep, there's a question on Zoom. So when I was referring earlier on about these S's and T's, you can just imagine that the program did whatever it wanted with this data. So these S's and T's could be literally anything. They don't specifically refer to anything in particular. Yeah. B is not pointed at the same spot as A. These are two distinct points in memory. So yeah, when I'm drawing it like this, just for everyone that's listening and watching, whatever, these are two separate chunks of memory. These are, if I want to denote that two things are pointing at the same memory, I'll find a way to like do like that or something and show that it's pointing, or it's somewhere off in the distance. It could be very close, but it's different. It's a different chunk of memory. Good question. Okay, so what then? So something else to point out, because it does matter, and you might kind of catch on to the fact that in these challenges we were doing, or in level 5 in particular, we're storing the flag at +16. That's kind of to make everything a little bit easier. And the reason we're doing +16 and not +8 is because there's actually more metadata right here. As of 2.31, libc 2.31, which is on Ubuntu 2004, it actually stores not just the next pointer, which gets stored in these first 8 bytes, but the next 8 bytes actually store this thing called key. So we'll say that is key. Just to show that that's 8 bytes, and yeah, hopefully that will be clear enough. And what is key? So key is, I don't know the extent to which does it matter for this level? I think it actually does. Yeah, it probably does. Maybe, no, actually it matters for a different level, which is correct level 4, where level 4 is currently broken, but don't worry about that. Okay, but so what is this key though? This is actually, does matter, and yeah. This key keeps track of basically, it basically denotes that A is free, and when it is, the fact that it is free, where it is freed in terms of Tcache, is that it's freed right here, right at, it's freed in association with this Tcache size 16 chunk. So the natural question to ask is, why? Why do we need to store this? Why do we need to basically store this? So like, okay, so let me step back here. So it makes sense that we store these zeros here because we're maintaining this linked list structure. So these 8 bytes do definitely matter because they tell us where the next freed chunk is, if there is an next freed. In this case, it's null, which basically means there isn't a freed chunk after me. But this kind of makes sense that, actually, you know what? Let's hold off on this key thing. We'll get there. It'll make more sense after I do free B. So quickly, let's take a look at free B. Okay, so what happens? What happens is the exact same process that happened with regards to A and the null. It's now going to happen with A and B. So what does that mean? So what that means is this A right here is some address, and I'm realizing now that we should probably start referring to this as an address where it's 2, 3, 4. We're going to just make this be 8 bytes because then it will make more sense. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Okay. So we have, we're just going to call A 8 A's to denote 8 bytes. And so what happens now when we call free B? So what happens is the exact same thing as that happened before. It's a very straightforward operation. It's an O of 1 operation. Yeah, it's a simple operation. So what happens here is that this A gets ripped out. That doesn't matter. Let's assume that that's stored in some temporary variable for us right now. And what gets placed here is the B's. So B, 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 I don't know. This is, okay, sweet. All right, so, and what happens next? The same thing that happened before happens. These S's, instead of getting replaced with zeros because 0 is there, well, now what was there was A's, so A's go here. So what does this mean? What this means is that we're maintaining a linked list. We've got our linked list data structure that allows us to keep track of all of the freed memory in this hyper efficient way. As Jan discussed, this heap implementation wants to be very fast. It needs to be very fast because you're potentially doing millions of these heap operations, and it needs to be as fast as it possibly can. And in order to make it fast, we're using this linked list because we've already got the memory. We've got this linked list. So let's see, what do I mean by that? What I mean by that, yeah, there's a question in Zoom. Yeah, so there's a question about key metadata. I'm gonna get to it in a bit. Wait, do I have 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7? No, we're missing one. Why does that look? No, maybe that is right. Okay. Anyways, so when we did this free operation, you're right. This key does exist, and I'm going to talk further about the key in just a moment. So when we did the free, key also ends up here. So what do we have now, though, in terms of this? I keep saying linked list structure, right? It's all these challenges are basically just understanding the linked list. Okay, so what we have now is this header pointer that is the beginning of this Tcache data structure that tells us where is available memory. So when we previously called our 2 mallocs, it was null and basically said we don't have available memory in Tcache for you to use. And notice Tcache, it's a cache, right? It's a caching mechanism. Okay, but now we do. And what does it tell us? What is this, if we were to understand now that all this data is in place, what does it all mean? So what it means is it's telling us that if you want a size 16 malloc, you can actually do it, and you can get these, you'll get these Bs back because we've cached it, we said it's ready to go, it's available. And what does B tell us is available? And as part of this linked list data structure, B tells us that A is available, right? Because you can look at the head of the linked list, it tells us that B is available. Now you go to B, and B tells us that A is available. And what does A tell us is available? Well, A tells us, well, nothing else is available. But you could think of that, you could have this recursive data structure going very far out of this linked list mechanism of chaining together all of these free and available memories, memory chunks. Okay, so now what happens when we call malloc of 16? What is going to be the result of this? Well, we're going to take a look here at our Tcache for size 16 and see is anything available. Is it null or not null? Well, it turns out it is not null. Something is available for us to use. So we are going to rip it out and store it here. This is going to be the result. But before we get our result, we need to do some further stuff needs to happen to maintain this linked list data structure. Well, what needs to happen is that when we're about to return B, in order to keep this cache consistent and working so that for the next person that calls malloc, we need to update our cache header linked list pointer. And how we do that is, well, we're about to return B, and B is going to tell us where the next thing that is available. So we go to B, we look at these first 8 bytes, which is 8 A's, and we move it into be the header of the linked list. So now we actually haven't modified any memory here as part of this malloc structure. I think that's true. Maybe there's some chance that this key gets changed, but let's ignore that for now. So we called malloc 16, we got these Bs back, and let's say we call malloc 16 again. The exact same thing happens. We go to Tcache, we see what's available. This tells us, oh, it's not null, something's available, A is available. So here's your A. And how do we keep our cache consistent? Well, we look at A, and we see the first 8 bytes, we take it out, and we move it here so that we can keep our cache consistent. So we're just maintaining this linked list data structure. So in this way, if you call malloc, malloc, free, free, malloc, malloc, only 2 regions of memory were used in this process. Okay. So let's go back real quick to before we did these mallocs, these last 2 mallocs, and quickly just talk about this key data structure. So I think it's become clear what these first 8 bytes are and why they matter, because they're maintaining this linked list data structure. But why do these, actually, hold on, there's a question in Twitch chat. What happens if you use chunk B before mallocing 16 bytes again? At the very start, so like right here in this state. I'll wait for that, but while I'm waiting to see if you mean at this point in time, let's quickly discuss why this key matters. So we clearly understand why the first 8 bytes matter because the first 8 bytes matter because this is how we maintain this linked list data structure in order to keep track of who's free as we free in malloc. Why does this key matter? So the reason this key matters is for the following reason. If we call free B again, this is very bad. And the reason this is very bad is because what theoretically would happen here is that we would get ready. So what happened before when we called free B? Just a quick recap of what happens when you call free. What happens is that you're going to update this with the address of what you're calling on, of what you're freeing on, and then you're going to go to that address and you're going to update it with what was previously there. So when this was a bunch of A's and we were getting ready to call free B the first time, we make this, instead of being A's here, we make it be B's here, and then we move those A's in to be the first 8 bytes. So what happens if we call free B again? Very bad things happen. So we're going to replace these 8 B's to be B's again, right? But what else do we do? So even though I say replace, right, technically nothing would have changed, but we pull it out and then we put the new value in. And we take what was previously there, those B's, and we would make that go here. And if you're thinking about this as a linked list, because it is a linked list, this is a very bad situation. What's going to happen now, every time you call malloc16, is you are going to get those 4 B's or those 8 B's back every single time. You can spam call malloc and every single time you would get this. The key stops this. So last year when we taught this course, we were on Ubuntu 18.04 as the most recent LTS, and this key actually didn't exist. So when you did this operation, if you did a double free like this, you would forever get a bunch of B's. Okay, so and also let me just clarify why you get a bunch of B's every single time. So what happens when we call malloc? Well, when we call malloc, we take the address that's currently available, right? That's going to be what's returned. So that's going to be these 8 B's. And how do we know how to keep our Tcache consistent so that the next person can get their correct chunk? Well, we go to those B's and see what the first 8 bytes are, and we take this, replace it with that, so now we have the next one. But as you saw, nothing just changed. This means that every single time we call malloc16 now, we're going to get B's back. And this is how it worked in 18.04. This has since been updated. It's been they've decided to make things more secure at the cost of, I guess, a little bit of performance or whatever. But I guess they've decided this performance overhead is worth it because this double free situation is very, very bad. And the reason, if you actually try this in one of the challenges, what you're going to see happen is that it's going to actually throw an exception basically, and the whole program will crash. In fact, we can very easily see that. That's probably worth looking at. Let me heap. Let's save this real quick. Let's run baby heap level 5 just to show what I'm talking about. Let's do malloc 0 for the 0th chunk. Let's do 16 bytes. So it gave us this. And then let's do free on the 0th thing. Okay, so we just freed that allocation. And what happens when we do free again? It detects it. Double free detected in Tcache 2, aborted. Previously, when we taught this course last year, this didn't happen. Everything went on in its merry way. Security has been upgraded. Emacs. And the reason that we're able to detect that is this key. So what happens when we call free B is that we actually check to see if we already are in Tcache. How do we check if we're already in Tcache? So this first time when we called free B, remember I said that this key gets written here. Well, guess what? All you have to do when you go and call free B the second time is just check to see if key is there. If key is already there, can you move the... Oh, wait, did you not see before? Oh, I see. Yeah, 1 second. Let me quickly, that's a good point. Let me hide paint real quick. Actually, we haven't been using paint in a while, so keep it hidden until we need it. Okay, let's just go through it real quick again to show what happens. If we do malloc 016, we get our allocation, and then if we call free 0, it frees it as expected. If we free 0 again, we get double free detected, aborted. It detects it. How does it detect it? Very simply. This key is what tells it that it's already happened. So when we go and call free B, what's going to happen is that the first thing we need to determine is what Tcache bin are we in. And how do we do that? Well, we look at the metadata here, and we look at this, what I'm calling this first dot, which is basically 8 bytes that tells us our size. So we can tell what size we're in. And that size Tcache thing basically has this key associated with it. And the key associated with it basically says, yeah, you're freed and you belong to this Tcache chunk. And that's how this key gets written there when we did that first free. And then when we do the second free, we check to see what size we are. So in order to know what Tcache we belong to, and now we know what Tcache we would go into. We know what key belongs with that. And once we know what key belongs with that, we can just check to see, before we write the key there, we can just check to see if the key is already there. And if the key is already there, clearly something bad is about to happen. We're about to get into this double free situation, which is an absolute disaster. For clarity, just to be, I guess, more precise, you could think of the situation in which, by complete bad luck, I'm calling this key thing that is 8 bytes, by some crazy off chance, since we were given this memory when it was mallocked and we were able to just do whatever we wanted with it, when we go and free it, technically the key could have already been there by some crazy chance based off of what the program was doing. And this isn't a double free. This actually was valid data that was there. So what actually happens, it doesn't just immediately say, oh, the key is there and abort out. It's actually going to go through this Tcache linked list, and it's going to walk the whole linked list and see if it's there. So the reason you don't want to walk the linked list every single time is because this is a slow operation, right? This is an O of n operation, whereas everything else we've talked about so far has been an O of 1 operation. But this is such a very unlikely situation that we're willing to pay the O of n cost performance to just be absolutely sure that this wasn't there by chance, by just walking the linked list to see if this was random, or if someone's actually pointing to it. So you could think that the very first thing, we're actually going to immediately get it on the first try when we do this second free, because all we need to do is look here and see that, hey, yeah, someone's actually got the B address ready to go to be already in the Tcache. But in the worst case, you would have to walk the whole linked list. So anyways, that is why this key exists. It stops double free, which is a very bad thing, because as we said, if you get a double free, now every single malloc is going to forever give you that same address until you do some other corruption to break that. And if every single address, every time you call malloc, it's giving you the same address, you have insane possibilities in order to corrupt metadata and corrupt whatever, right? It's not a good situation. So as of Ubuntu 2004 with libc 2.31, they've added this key element. Hold on, my headphones are starting to die. They've added this key element that is able to check that. Okay, so what I've just gone over and rambled through for the last 50 minutes or whatever, however long, is everything you need to understand in order to solve all of these levels. Everything just comes down to this linked list. And what do I mean? Okay, so what do I mean by that? Maybe that sounds too absurd. Yeah, there's a quick question in Zoom. Go for it. Yep. This right here is the start of the linked list for Tcache size 16. Yep. Initially null. Yep. Yeah, and then so this, you can think of this linked list as a first in, last out. So in the same way as a stack data structure. So every time we call free, this gets updated, and yeah, so when we called free of B, it's not like we walk the linked list and put B at the end. We put B right at the start so that the next person that calls free, or the next person that calls malloc 16, is going to get the B address. It's not going to get the A address because it's this first in last out data structure. And yeah, it's a linked list, exactly. Okay, so further going along with why do I keep saying that everything is just a linked list? Like, all you need to understand is this linked list operation, because as this is happening, there's various memory writes and reads that are happening that are controlling further memory reads and writes. So this is like, this linked list operation gives you read and write primitives, and it gives you, as a result, potentially like control flow primitives. Okay, so some things to pay attention to. So someone said earlier in Twitch chat, what happens if you use chunk B before mallocing 16 bytes again? So this is a use after free. If we modify the contents of B, which we've promised we're not going to do, the program is basically saying, hey, I am done with this memory. It's very bad programming practice and against the heap implementation contract to continue to use this memory, even if it's not technically going to give you like a segmentation fault. And the reason it's not going to give you a segmentation fault is because if you did things like that in order to make that happen, there's insane performance overhead in order to like deallocate the memory or something in order to make a seg fault happen. And it's, yeah. So we've just got to agree that we're not going to use it. But if we do use it, say we change these first 8 bytes here. So let's say we do like B, we'll use some Python syntax. Hopefully that's okay with everyone. And we make that be 8 C's, right? So we use after free. We modify this memory after the fact that we've freed it. Well, what's going to happen, as this operation, this Python-ish thing says, is that now we've made this happen. Okay, so we've got our 8 C's. What's going to happen now is that we've just influenced what's going to happen as we call malloc and free. So if we call malloc 16, nothing's changed in terms of us getting B first. So the first thing that's going to happen is we're still going to get B. We haven't actually influenced that from not happening. But what's going to happen here is that now we're going to look at B. We're going to say, what are the first 8 bytes so I can keep my cache consistent? I might have an extra C in there. We want to keep our cache consistent so that the next person doesn't just also get B or something, right? We want to update our linked list. So the next thing available is going to be these 8 C's. So what we see now is that if we call malloc 16 again, we're going to get these 8 C's, right? And we just influenced by using after free where this malloc 16 is going to end up. It's going to give us these 8 C's instead of 8 A's, as would have prior done. And this has all sorts of implications. And also something to note is that in doing this, we also actually... so when we get these 8 C's, we actually need to also still dereference these 8 C's. And we need to look at the first 8 bytes of them. And let's assume that there's like 8 D's there. Actually, hold on. Maybe this is... Let's assume this like fake chunk that we've just created now, which we're going to call C, has like... Oops. 0. Whatever. This fake chunk that we've just like brought into existence by overwriting the first 8 bytes of B with C's also has some stuff, and we're actually, when we give out this C address, we're going to have to actually still look here as well. We're going to have to see like, oh, looks like we're going to have to dereference C, which means that if C is not a valid memory location, that we're going to segfault here because we're about to dereference C. But if we can assume for a second here that C is a valid memory location, then we can look at it, and now that's going to be the next thing. And we're right now, the heap is going crazy. Hold on, let me make sure my headphones aren't dead. Okay, I can hear you, perfect. Yeah. Okay, so the question is, it doesn't seem like we have the ability to set the value after we malloc. So I think you said you've been looking at level 5 in particular. Level 5 doesn't give you the ability to just arbitrarily overwrite it. Like to basically be able to do this operation that we used in order to influence this from happening. But later levels actually give you a scanf primitive. So you can call scanf and you can write arbitrary memory there. And that's where this will become highly relevant. But so let's actually, so I think we hopefully now at least kind of understand what's going on with Tcache, and like I keep saying, that it's all just this linked list thing, and this linked list really matters because, as we saw, for instance, in this case, if we can do this sort of operation, we can make this happen where we actually control the result of this malloc. But there's other things we can do. We can chain together mallocs freeze and use after freeze in all sorts of weird ways. So one of them would especially be relevant to level 5. So if you think back to level 5, which we were looking at before, let's actually quickly look at it again. Remember, we were doing this read flag operation, and then we wanted to do this puts flag operation, but we couldn't do it because the first 8 bytes were 0. Well, the first 8 bytes are 0, but we've been discussing a write primitive that lets you overwrite the first 8 bytes of memory, right? And make it something other than 0. Like, this is all just the linked list. So if you can transform this problem, actually, hold on, let's save this again. Let's stick to what we were looking at before. If you can influence this buffer, okay, so read flag gives us this address. So how you want to basically change the first 8 bytes of this address. And in theory, if there was like a free underscore flag operation, you might very clearly see how you would do that. If you could call free on this address and Tcache was already set up, so hold on, let's quickly, we're going to keep jumping back and forth here. So if we have, let's just throw some, what do we want to do? Let's say our current heap looks something like this. Actually, we want to keep the B thing. Yeah, okay. Let's go back to this state. Okay. And we did this, and this would now be pointing to 8 Bs. Okay. So what's this? What's the situation here then? So the first time, if you think back, actually, let's even go earlier, when we called free of A, we overwrote this with 8 zeros. So we clearly don't want, in this level 5 instance, to rewrite the 8 zeros that are already there with 8 more zeros, right? We need to make it something other than 8 zeros. But the reason that this wrote 8 zeros, whereas this wrote 8 A's, is that something was already in Tcache. So if you do, let's save that. So what am I saying? If you do read flag, if we were to somehow have this free flag operation, which doesn't directly exist, if we were to have this free flag operation and we were to call it right now, well, we'd actually just be writing 8 zeros still to the front, because that would be the next Tcache operation, but then we would take this address, right, and we'd make that be the head. But either way, we didn't actually alter the first 8 bytes in a way that we wanted to, right? We just changed it from being 8 zeros to being 8 zeros. But if something was already in Tcache, say 8 A's or whatever, then when we called, if we called free flag, which obviously doesn't exist here, if we called free flag, the first 8 bytes of this would be changed. If Tcache currently was pointing at 8 A's, the first 8 bytes of this would now become 8 A's. And of course, Tcache would also be updated to reflect this address. So we can see that going back to this is all just a linked list, and all of these challenges are just using that linked list to your advantage. We can use this linked list to like perform like this non-zero write. Even if we can't do an arbitrary write to this first 8 bytes of this address, we can make it be non-zero by using and abusing this linked list structure, because a pointer needs to, when we call free on this, become the first 8 bytes of this. Now, as I said, right, we don't directly have a free flag function, but based off of previous levels, you should know how to get this address under your control, maybe not your direct control, but in a way that you have the ability to do a use after free. So how do we do that? As a recap for prior levels, and we'll just do it for this level as well. If we call malloc, and this is the important size, so we're very interested in the linked list data structure for Tcache as it relates to size 376. So that's probably the world we're going to operate in. If we called malloc 0376, so to make our 0th allocation be 376, we can see that this is the address which comes back to us. Now if we call free, yeah, there's a question in Zoom, go for it. Yeah, exactly. So the reason we're calling this before read flag is, as I was saying before, there's no free flag function. We need to be able to do a use after free. And we can do a use after free as follows. If we now call free 0, right, we know that this is going to call malloc 376. And as I've been talking about for the last hour with Tcache, is we know what malloc 0376 is going to give us now. It's going to give us the head of the Tcache linked list. And what is the head of the Tcache linked list? It is this. So let's confirm that. If we call read flag, we are expecting that we will get this address back. Actually, we don't even need to, well, yeah, fine. Let's see that. If we call read flag, we get that address back. Right? It's just using the Tcache linked list, looking at the head of it, seeing, hey, this is non-null. I want to use this now. Okay. And so now, do we have the ability to do free underscore flag? Yes, we do. Even though free underscore flag doesn't exist, free 0 exists. And free 0 is still pointing at this address, allowing us to do this use after free. So if we do free 0, this isn't going to immediately make things work. But what just happened here is that we went to this address and we said, okay, we're going to mark you to be freed. And how are we going to mark you to be freed? Well, we're going to make the next we're going to make the head of the Tcache linked list be this address, and we're going to go to this address, and we're going to make the first 8 bytes be whatever the previous value of the Tcache header linked list was. As it turns out, after we did a malloc free read flag, at this point in time, Tcache is empty. So when we call this, we just made it so that the head of the linked list is this address again, but the previous one was null, so we actually just made the first 8 bytes of this be null. And as I talked about before, if something would have been in there, that would have been the first 8 bytes and have been made non-null. And just to show that this is still, again, going to be the head of the Tcache linked list, if we do malloc 0376, we're going to get this address back again. And we can even, actually, whoops. Hold on. Let's see what happens. Oh, this is so sad. Okay, fine. We might have ruined things by whatever we just did. But let's see if we get that same address back. Yeah, we do. Okay. We didn't ruin things too bad by whatever happened here. We can see that, again, we got this address back. Now, what happens if we call malloc 0376 again or whatever? Well, we're going to get a different address because it's null. But if you keep track of what the structure is of this linked list and what it is that you want to achieve doing various operations, you can basically do either arbitrary reads and writes, or like in this case, we just need to do a non-zero write. You just use this linked list and the various operations, which are malloc and free, to control this linked list and its read and write operations to basically get all of the flags for this module. We're basically using the metadata to, exactly, you're using the Tcache linked list metadata as well as like this use after free concept to basically have potentially arbitrary control over further Tcache operations, which gives you arbitrary reads and writes and stuff, yeah. Yeah. Yeah, let's take a quick... Does level 5 make sense now? Okay, because so something to clarify, because I've actually gotten questions from several people on this. You don't need to do like some crazy like chunk overlapping insanity to make this happen. Honestly, I don't even know exactly how I would do that sort of attack. I really don't know heap that much. But I do know linked lists, and all of these challenges are just linked lists. Okay, so let's take a quick look at level 6. Run challenge. Okay, so what does level 6 do? Okay, so this is, it tells us we have 16 unique allocations. There is a secret stored at this address, and we can quickly see that that doesn't change, okay? And the reason it doesn't change, of course, is because no PIE, and this is probably a global variable, and in fact I can tell you it is a global variable. So there's a secret stored at 0x42269. If you can leak out this address, you can redeem it for the flag. So as I was saying before with this scanf operation, once you have the ability to do arbitrary writes onto these as use after frees, you can like really control what's happening. So in level 5, we don't have this scanf ability. But fortunately, all we need to do is make something be non-zero, which we can do by just making it write a pointer, some random pointer, who cares what it is, as long as it's not a null pointer. In this case, clearly we're targeting something in particular. So you can imagine a scenario. Let's see if I can do Emacs heap. We can imagine this scenario where, as we were talking about before, if we were to overwrite this first 8 bytes with C's, or you could imagine it being this address, but let's just say C's for now. If we can overwrite this to be C's, so what does that fundamentally mean on like a memory level? Where in our diagramming in Emacs, this is the memory level right here. What that means, oh wait, we didn't write this correct. If we make the first 8 bytes of B be C, so what does that mean on a memory level? And especially in this T-cache context. Well, what that means is that we're replacing these 8 A's with 8 C's. Okay, which means that when we call malloc 16, we are going to check here. We're going to get 8 B's, and then we're going to look at B. We're going to see what are the first 8 bytes here, and we're going to update our linked list header with that because we've already used this. We don't want someone else to get 8 B's. We want to move on to the next chunk that's available. So now if we call malloc 16, we are going to get 8 C's. And in doing this, we're going to dereference C. If we could imagine, of course, that there's going to be some chunk of memory at C. Of course, in doing this, if C was not allocated, we would segfault here because we need to dereference it to figure out how we're going to update this value. But we can imagine that maybe who knows what's here? Maybe there is a secret here. Secret, is that 4, 5, 6? Maybe there is a secret here. Right? So now we did this. When we got our C's, we needed to look at C, and we needed to update this address, which you could be thinking in your mind, or actually there's only 8 bytes that gets taken. You could be thinking in your mind, oh boy, if I call malloc again, something bad's going to happen because secret is probably just ASCII data and it's probably not an address that can be dereferenced, so hopefully we don't call malloc again. But just don't call malloc again. You can now think, well, what can I do? Well, if I have the ability, and I just got this C address, and we just said that, oh look, the C address has a secret in it. Well, now when I call puts on this, which we just got back, which is going to be like, say, allocation 8 equals this, right, in terms of the levels, right? Then we call puts on allocation 8, right? We just now look here. Well, what's the data here? Well, the secret data is here. Well, we just now wrote to ourselves some secret data. There's other things, though, to pay attention to in terms of, I mean, you can go crazy with this in terms of what's possible. So even though I said, for instance, that this is an issue, that we can't call malloc again, well, we still can call free. Well, we don't actually have access to a free. But suppose there was some malloc beforehand that we had called that was like 16, which equals like, I don't know, let's come up with some cool letter, like G's or something. And then we go on and we call like free on this G address or whatever, which hadn't happened before, but now we're doing. Well, now what's going to happen here is we're not going to crash. Everything's fine. What's going to happen, though, is this is going to get copied. Notice how I use the word copied. It's going to be copied, let's say, to a temporary variable for this right this second. because that's how this works, right? So if this is what the Tcache looks like, right? How do we update Tcache? This is, as I keep saying, everything's just this linked list of Tcache. This is all you need to wrap your head around. And maybe it's going to take a little while and you need to like mess around with it for a bit. But this is the fundamental idea you need to wrap your head around, is all of these operations and what they mean. Like they do a specific thing, and then you can assign some abstract notion to it, and I'm assigning the idea of it copying here. And so what do I mean by that is that we need to update the Tcache linked list header. How do we do that? Well, we just called free on these 8 Gs. And actually, hold on real quick before we go too far. Let's assume that this G address is good to go, and that there's, I don't know, let's just for now say that there's 16 zeros. We can't do that. Let's say there's 16 O's. So what's going to happen is that we just freed this. So this now needs to become the head of the linked list, right? But what happens with this that was sitting right here is it gets moved right here. Right? So this is just copied in some sense, right? You could think of it as at one point in time, C was pointing to secret, or C at address C, there was secret AA, right? But through a combination of doing this insane, like overwriting B to now BC and then malloc to make it so eventually it's that secret data was sitting here as being the next in line in the Tcache pointer, and then we call free on G, that we actually, through all of these operations right here, well, maybe I guess all of them are highly relevant to this happening. Through all of these operations, though, so before C contained secret AA, and maybe it probably still does. I'd have to think about it. Maybe I missed something, but I think it still contains it. Yeah, I'm almost certain it still contains it. But we also just moved it to like exist at G now. We actually just did a copy, right? Does that make sense why this is a copy operation? That like we just kind of like moved it through the linked list and then moved it back, and then like now it's fundamentally been copied, right? Because at some point, yeah. Exactly. So you can think of it as when eventually we called malloc to get these to get C. When we called malloc to get C, we had to copy these 8 bytes here when we were given this to be the head of the linked list. And we did that because that's what happens when you call malloc, is that so previously there was 8 C's sitting here, right? We called malloc, and that's how we got C back, but we need to go to the next element of the linked list. So we're going to return the C's because that's the next thing, but then we need to go to the next thing so that the next person that calls malloc can also get their own thing, the next thing in this linked list. And that was secret. So in some sense, we just stored the secret as a temporary variable inside of Tcache here. And then we called free after the fact. So currently we've kind of like made this temporary variable using Tcache to store the secret. And then we call free on the G address. So in order to make that happen, what we want to do is that we're going to say, well, okay, the next thing that's going to be available is G because you just freed it. We just freed G, so the next thing that's available is G. And then we need to go to G, and we need to say, okay, well, once you're done, what's the next element? Well, it is secret, right? So we've kind of can imagine like this linked list is like rocking back and forth, and like data is being copied and moved around in order to maintain this linked list. And effectively through this series of operations, we just did a copy. Now you don't necessarily need to do this in level 6, right? I'm just kind of showing you what's possible using Tcache linked list and doing all these various operations. Does that make sense? Where? Say that again. Zero. Oh, yeah, this is just like somewhere in memory, right? Yeah. No, so the free list, in some sense, right, is just one pointer, right? The free list is just a single pointer, but it's a recursive data structure, and the single pointer points to the next thing, which points to the next thing, which points to the next thing. But in terms of like this like mass or this like overwhelming global metadata that's maintaining the heap or whatever, it's just one pointer. That's all you need. It's just this one pointer. And then that pointer will tell you where the next pointer is. Not necessarily, right? Due to, so in general, if you correctly use the heap, right, this would have all been on the heap. But in this case where we did this overwrite here, right, and then we basically, by doing this overwrite, we managed to make malloc actually return 8Cs. This doesn't have to, these 8Cs as an address, they need to exist, but they don't have to be on the heap. They could be anywhere, right? They could be on the stack. They could be in the global data. They could be like anywhere that's not going to cause a segmentation fault along the way. So even though the malloc is returning this to us, right, we've kind of abused the heap into making malloc return this. But in general, right, if you don't abuse the heap, yeah, this would like, for diagramming purposes, this is just like memory somewhere. But yeah, like, yeah. So what the notation here I'm trying to use is basically saying that this is the data at location A. So at location A is this data. At location B is this data. At location C is this data. Yeah. And someone asked in chat, what command do you use to do that overwrite? So it's not, this command isn't available in all the levels, but we were looking quickly at level 16. And in 16, we actually have the ability to do this scanf operation, which actually, as it turns out, doesn't give you strictly arbitrary overwrites. So let's actually look at this real quick. If we do, maybe it'll actually be worth using pwn tools real quick. Import pwn, pwn process baby. Because this is actually, there is a limitation. This isn't a read syscall, right? This is a scanf, which has some restrictions on it. If we do proc equals this, and let's assume that we want to do, let's do send line, let's say malloc 0, size 6, or let's even go 64, just to make sure there's room or whatever. If we do malloc 0, 64, and then we did like send line, scanf 0, so this means we're about to write to what just was given to us, and then we do like, let's say 8As or whatever, and notice that this is send lining, so there's like a new line at the end of all of these, and then we do like proc read 4096. Oh, right, so this is where we are. We called scanf and wrote into it. But now if we do proc.sendLine puts, and we want to puts 0 to see what the data is that's there. So we just theoretically, correctly I'm sure, sent 8As. So puts 0 should show us that we have 8As there. And we can see, in fact, yep, there's 8As there. But scanf actually stops on particular characters, right? So scanf will stop on a new line. So if you were going to do, let's do scanf again. And we can actually see, let's see if it stops on, say, a null byte. Let's do AAA, and then let's do like a null byte. I actually don't know what it's going to do here. Let's see if it captures that null byte. Oh, but the puts would stop there either way. So maybe it's writing it, maybe it's not. So yeah, it's something though to realize is that we're using scanf and puts. We're not using read and write. which means that, like, for instance, if we write in this null byte, even if these b's do get copied into memory, when we eventually go to do our puts, it's going to stop on this null byte because it's a null terminated string that puts is looking at. But other things it's going to stop at is, so for instance, basically any, as we're scanfing, basically any white space character, because as you saw here, we're doing a scanf %72s. This is going to stop on any white space character. So if we do, actually, let's say like this, right? So this is a white space right here, you can see. If we wanted to send this to the program, actually, let's make this even more clear because there were already A's there. Let's do like CAB, and then let's read. We can already see that something went wrong. Unrecognized choice, unrecognized choice. It turns out that it was actually looking at A and B as like operations that we're trying to do. If we, just to even further show that though, if we do puts of 0 and read what happened there, only the C's ended up there. These A's and B's, the scanf is stopping on this space. And something to think about, like why this matters, right? Because you're not actually interested in typing out a sentence and being able to put your sentence or whatever, who really cares, is that if your address contains one of these white space bytes, so space, right, these are all just stored as bytes, right? ASCII doesn't really mean anything other than as a convention on what like symbol to display on your terminal and wherever else. This is just like it's hex 20, right? So if your address contained hex 20, hex 20, this would be bad, right? If halfway through your address there was a hex 20, because then there would be issues in terms of being able to do a scanf to get that in. Fortunately for you, we've designed these challenges very carefully so that if this is an issue for you, it's intentionally an issue for you. I don't remember which level, but one of the levels is intentionally going to introduce a white space character into your address to force you to think more creatively on how you overcome that. Okay, is there any more questions? I'm going to probably start wrapping up office hours. Yeah. So I guess what I was trying to show off, so the first thing I did is just malloc 64 bytes so that we have a chunk of memory to be working with, and then we just continue to work off of allocation 0 from here on. So I did a scanf 0 and sent 8 A's, and we can see that it's doing scanf, taking that in. And then when we did this puts 0, after we sent it, it's 8 A's, trying to basically make whatever the address was that was here, which would be this address right here on the heap, the first 8 bytes of which we just made A's. When we puts it, we can see, yep, in fact, we get to see those 8 A's exist. But if we do a scanf again, so we did scanf before, we sent 8 A's. We do a scanf again and we include white space characters in the data that we're sending. We're going to see like these unrecognized choices. And the reason for that, if you look into the like a man page of these format strings and how they work, is that this will actually stop at the first white space character. So even though, like what I mean by that, so before the reason it actually stopped here is because we did send line, which means there's a new line character at the end. The new line character is a white space character. In this case, we have a space as the first white space character we're going to run up against. And we can see that we have 2 unrecognized choices, one for each of these, because as it turns out, these this like while loop that's doing this is also using scanf to determine what operation to do, so that it also stops on new line character or on white space characters. And just to further illustrate that, when we did puts 0, we can see that there's only C's there, that these A's and B's didn't actually make their way into memory. because the thing to realize is that whereas in most previous modules we just directly worked with read and write syscalls that just whatever the size is, that's the size. In this case, we're working with like puts and scanf, which puts is going to at a bare it's I think it'll only stop on a null byte, but it'll stop on a null byte, which means you can't if you're interested on outputting data that contains a null byte and then more data after that, that's not going to work. And scanf, when we do this scanf with this %s modifier, will just stop on any white space character, which means if you have a white space character in what you're trying to send, it's not going to make its way into memory. This, by the way, this issue that I'm talking about is more relevant in future levels. In level 6, this isn't going to be a problem because we very carefully designed it in a way where it won't be. What I mean by that is this address here, you can see right here, you can see the bytes. So this is the address, and you might imagine that at some point you're going to want to scanf this address into memory somewhere. None of these bytes are white space characters. But you could imagine if instead you got unlucky and like this was the address, you would have an issue, because when you go to send hex 20, so for instance, let's say let's just show it in Python because it'll very quickly show us the ASCII. If we, and this isn't little endian, let's quickly, just for sake of sanity, make it little endian. If we were getting ready to send this address somewhere, you can see there's a space here, and this is like the same issue here as the space. But this level here does not have this issue. A future level will have this issue intentionally, and that's part of the challenge. Okay, so I see, or is it with 6 that we put whatever we want in the given address and then enter that into the secret? Yeah, there's all sorts of options, and future levels explore all sorts of ideas. That's definitely an interesting idea. All right, any final questions before I end office hours? There's currently 10 released. If we release more, it'll be tonight, and there's a decent chance, because we actually messed up a couple levels, that a couple more levels will come out. But yeah, so potentially 12. But the final levels will be released tonight. Yeah, I mean, depends. Yeah, sure. I mean, the free list is part of the heap, but yeah, it's just a linked list that does various memory operations. Okay, I see one more question in Twitch chat. I'm still confused with 6. What are we supposed to do with the address then? Well, you might want to, I don't know, watch earlier in the office hours, but oh no, that's not right. Emacs. I've very clearly talked about things you can do to abuse Tcache and influence stuff, right? I'll very quickly go over it, and then I'll end office hours. Imagine that you're in this situation here. Let's just do that. And imagine that address C contains some secret that you're interested in getting, and you make that address be the first 8 bytes of B, and that at this point there's B is currently sitting as next in line to be malloc. Well, when we go in malloc and do 16, you'll see that we get 8 Bs because this is the address here. We delete that because that has been now given, so we need to go to the next element in the linked list. What is the next element in the linked list? Well, we just overwrote B with 8 Cs, and that is how we've decided what the next element in the linked list is going to be. So now when we do this, we just got B, so you can kind of think that maybe we don't exactly have arbitrary control over what's the result of malloc. But on this next one, we do have arbitrary control over what is malloc because we just wrote 8 Cs here. So when we do this, how do we determine what's next? Well, we look at the Tcache head. We see, oh, look, it's 8 Cs. We pull that out. We say this is the result. We go to C. We take the first 8 bytes of that, and we say that's next in line. So it's just this cycle of linked lists being updated and pushing and popping basically off of this linked list in terms of keeping our cache consistent. And if you do various use after frees along the way to mess with this linked list in terms of what the next pointer is, you can do all sorts of useful things. And now maybe you might think of a use after, well, now you don't even, this isn't even a use after free. Maybe this is allocation 8. Maybe you're very interested in the data here at allocation 8 and you might want to write it out. Maybe, you know, something like this would be very cool, because if we do this, we would look at address C. And what's that address C? Well, there's some very useful data that we might want to write to standard out here. How do we look? Yeah, there's a question in Zoom. Go for it. No. I'll just read the Twitch chat after. Go for it. Are you talking about right here? So right at the start, the reason that we got these 8As, we don't have control over these 8As. Basically what happened is at the very start, there was 8, we're just gonna use, no, there wasn't 8As in the free list. It was actually just empty. So when the T-cache is empty, you have to use, the heap will use a different mechanism in order to get that memory. The T-cache is relevant when the T-cache has data, which is you're gonna at least need to free at some point before the T-cache will have data. So for this first A and this first B, some other heap mechanism is what gave us this data. It wasn't sitting in the T-cache yet. Once we free it, of course, that's when the T-cache comes into play, and now we've got data sitting in the T-cache. So just think of a random program, right? Just imagine this is a new program you call malloc 16. The heap promises that it's going to give you some data, right? I mean, assuming there's some data to give or whatever. It's going to find a way to do that. The first thing it's going to do is it's going to check out T-cache, which, as the name implies, is a cache. It caches available memory, but that doesn't mean it's the only place for available memory. And it's going to see that this is null, it's empty. So it's going to just use a different mechanism within the heap in order to make some memory for you. And when I say 8As, this is the memory it finds to give to you. And it's not using the T-cache to give you these 8As. You can imagine maybe the heap is implemented where maybe it just has like 10 megabytes of data just chilling. And maybe the very start of this 10 megabytes of data just chilling is the head of this address is 8As, and we give you your 16 bytes, we give you your 16 bytes by just breaking off a chunk of this 10 megabytes of data, and then maybe, so you could think of, instead of this T-cache size 16 here, maybe there's just like heap data equals a, and when this is null, this is empty, it'll just instead look at this pointer and be like, okay, well, the next thing available is the 8As. We've got 10 megabytes of data, so we've still got plenty. We can give out 16 bytes, no problem. We give it our 16 bytes, and then we just update this to say instead we're 8As plus 16 or maybe 24 to account for some metadata. So that if someone else asks this particular part of the heap for data, now we've got 10 megabytes of data minus 24 bytes available, and yeah, we've still got stuff to give out, right? So this is maybe how the further into the heap works when there's not space from the caching mechanism. But T-cache is specifically relating to the caching mechanism, so the first time you call malloc, you're not hitting that caching mechanism because there's nothing available in it. Does that make sense? Yeah. The heap is this insane algorithm that does all sorts of insane things, and the T-cache is just one part of that, and it's a caching part of that. for these small sized allocations. So for instance, if you allocate, like, if you say like malloc 10,000 bytes or whatever, the Tcache isn't even going to come into play because the Tcache stops at sizes like less than, like, I don't know, 1032 bytes or something. If you ask for 10,000 bytes, a different part of the heap implementation is going to do that. This is just, as I keep saying, one part of the heap implementation, but it's the part that we focus on in this module. Okay, so there's a question in Twitch chat. How do you look at the Tcache head in the challenge? You don't, there's not necessarily a super great way. I guess in GDB, this is probably going to look terrible when I do it in GDB, but let's do it just for the sake of doing it. Yeah, this is going to come out terribly, but well, maybe it's not completely terrible. Okay, let's just continue. Oops. Oh, this is, we need to do this one in practice mode because it's sranding on the, it's sranding on the flag, and when we do GDB like this, it's failing to do that. Let's re-enter as practice. Eventually. Okay. Oh, whoops. Let's do, let's just become root. And then let's do GDB. And let's start. Let's just hit continue. So let's just do malloc 016 and then free 0. And then we hit Control C to just go back into the GDB context. And now if we do, I think pwn.debug has this mechanism that actually shows you some of the stuff at play. It also has Tcache. I don't know if this shows you the address of the head, but this definitely tells us that this is the next in line thing for this particular size. It's kind of telling us there's one element in here. If we do now, if we continue, so just remember this address, like it ends with AC0 or whatever. If we do malloc 032, oops, hold on, was I doing size 30? Let's restart this real quick. I don't remember what size I was doing. I think I was doing 32 though. Start, continue, malloc 032 gives us this address, which ends, I guess, with AC0. And then let's do free 0, Tcache bins, ends with AC0. Oh, yeah, so this is round, it's, I don't know exactly what this is, but you can see that I did 32 before, and this is like 48 or something, so I'm not exactly sure what this value is. But anyways, so we can see that from Tcache bins that this is kind of next to be allocated. If we hit continue, and then we do malloc 032, we can see in fact this is what's given. If we quit out again and do Tcache bins, we can see that it's empty, which means that if we do malloc 032, oops, we want to do that inside the program. Malloc is some sort of operation here as well. We can see it gives us this address, and then let's say we do malloc 132, and then malloc 232, and then malloc 332, and then let's do free 0, free 1, free 2, free 3, and then just look at Tcache bins. We can see it's like showing us this linked list, and like we can definitely see that if we do xgx at that address, what are the first 8 bytes. The first 8 bytes are this, which, right, as we keep saying with this linked list data structure. And just to also show you the key, this is the key, which is also like this heap address. And I think this heap address actually shows the number of elements. Maybe it doesn't. I'm not sure what's actually here. But this is the key. And you'll see that all of these actually have that key value. So if we do x2 gx that, and x2 gx that, we can see, so this one is right here, points to here, and contains this key. And then we looked at here, which points to here, and contains that same key. And then just to show one more, if we do this, it points to the next one, which is here, contains the key. In fact, let's just do the last one just for sanity. This, and we can see that this says it's the end and has that key. Okay, let's see, what else is it necessary? So it's not necessary to strictly know like where this Tcache head is located, but you should definitely understand, you should be able to, that's not right, Emacs or heap. Basically, in order to solve these levels, oh, I misroot. In order to solve these levels, you're gonna wanna be able to do conceptually in your head / with a piece of paper, you should know exactly the memory that's going to change as a result of doing mallocs and frees, and start to build up an intuition of how to abuse it to achieve your goals. Okay, I'm going to, on that note, wrap office hours up. So thank everyone for joining. Yep. Yep, no problem. All right, goodbye everyone. Good luck with the challenges.